Okay, thanks very much for the invitation. It was really a nice conference so far. So, a nice. So, I want to talk X algebras via convolution behind this grammar. Just start with the motivation. So let's say we have C and a Boolean categories are enough projectives. So I think of what we do about from algebra A. I take the compose the projectives lambda, and I want to take the endomorphism minimum sum of them. So I have this slop in the index that come outside, etc. No, don't care about this anymore. So we want to describe this algebra. Of course, there's many samples. Okay. So there's of course many examples when we know this algebra. For instance, if you take harmonic O, or ordinary O, there's diagrammatic or something marvelous, or there's or lots of diagrams, so and this is not. And of course, we have this in our website, which we use to our application. So we know such things, but to do something very different now, I want to assume that my category is spaces. So we have standard objects, we have deltas, or we can call them gamma models, or we like super objects. So in this conference, we can call them constants, and I want to understand what is this. Okay.
Catharina, I don't understand when you say there's a description of some decomposable predictor. Like in all those examples, the predictor generators are different predictor generators.
Oh, in these things, you might maybe take the momentary. Yeah. Okay, I don't go to the right hand.
Okay, fine.
So I just want to say this is sort of simple to understand why it is. But yeah, I want to go in this direction of the X algebra standards. So let's first think about what is the dimension of this. On the left-hand side, we know dimensions of these home spaces are given by kind of harmonic resonance polynomials. So let's look at the right-hand side. At the right-hand side, there's this whole conjecture of Gerber and Schuster that these dimensions of these algebras are given for category O by the so-called polynomials, which are actually polynomials which can be used to define customers polynomials. But very soon after the conjecture was formulated, it was shown that it's not correct. And then in a more recent paper, it was shown that for harmonic, no, not convolution category O, this dimension are given by so-called algebraic polynomials. That's the paper of Tubbenhauer and Oded Yacobi. These algebraic polynomials are, for me, still a bit mysterious. It's a combinatorial classification, but it's not yet a nice geometric way to understand. So why would we care about describing these algebras? Of course, in the first case, your category A is not useful this algebra. In the second case, your derived category is equivalent to modules over the website. But unless we be very careful, and this is something which some people like very positive about. For instance, in Mathas talk and in the panel discussion, that we really have to put this in a BG or infinity setting to make an equivalence of A infinity. And we don't expect that this thing is formal necessarily, and so we would like to understand this very structure. Okay, so what is the motivation from categorification? So if you think in terms of a lot of homology, you want to categorize my lines is principle that of 2 QS and 2 principle that of natural expression, and also understand taking depends on workers. And the observation here suggests that this map of taking the principle that behaves well on the standard basis vectors of the natural expression. So we just blend the standard basis vectors together to get the standard basis vector. So it also behaves well in the categorification setting on standard model. So that means if you would like to understand principal product, it might help to understand this X algebra or this standard objects together with its higher function. So now what I want to do today is I first want to give an abstract geometric general setup, which is towards this understanding of this algebra E. Then I want to make it a little bit more concrete in a more algebraic sense for Grassmannians and Grassmannians. And at the end, I want to do something which is diagramatic, and so I hope everybody who likes at least one of the three papers. And you should listen to the one which you don't like yet. Okay, so let's start with the proper setup. So K is an algebraic enclosed field, and today I will always trust in K to be C. But everything which is geometric works over algebraic enclosed fields. And everything which is category O will work over C. And because I anyway forget that K is arbitrary and mine C, I want all this. Okay, good. So what do we have? We have that the smooth projected like line by. Point that my C star acts on Z with finite remaining finally many isolated fixed points. So what is examples? Examples. Keep in mind is G mod P, that G is a reductive algebraic group, P is a parabolic, and of course all the action of G inside P we have the parabolic, and then the tools and the multiplication, and inside the star, the C star, I just choosing a regular copy. So GLN vectors somehow embed T into the focus, T to the A1, T to the AA, and A1 and up to AN should be generic digits. Okay, good. So then, what is the fixed point? The total fixed point is taken as some starting point, and these are just the coordinate fix. That means subspaces in this flex that was generated by coordinate basis vectors, which are picked in my ambient space. So that's the first example. And for later, because I want to do later combinatorials, just do the example of the Grassmannian to form what are the coordinate subspaces in this case. So just span two-dimensional subspaces in C to the 4, spanned by two standard basis vectors, I and J. I is not in J. And I can draw pictures like this. So I have 4 basis vectors all together, and I pick 2 of them, which are blue ones. And so I have all together 6 scores. Make sense? Okay, good. So, second example, which I want to mention now, we have this. So what is this? It is G mod P, and inside I take fixed points under X, and X is a unipotent. Or no, I should say unipotent. For GLN, it's just a unipotent matrix, which you take. And so I want to mention just one of the effect. So this is the AD easy alignment singularities. So I just draw the picture of type A, finding similarity. But just exclude S2s together or P1s. In this case, my unipotent is, or unipotent is of the form I have unipotent is one Jordan block of size n minus 1 and one of size 1. And I add like this. Everything inside matrices of size n. So I get this Klein singularities and those fixed points are just this connecting points. Okay, so that's a good example. So now I want to take these and do this abstract nonsense of these standard objects. So what I want to take is I want to take the set of each spots. Spots. And then I want to take C plus and C minus. So this is for me the attractive angle. Or attractor. And this is another cover. So let me just say it abstractly. So this is a scheme which is represented by the following thing. I take columns from some scheme S, and set 0, well, of course, this one is columns style rebellion on the S set. And then plus and minus. Nothing else that comes from an A plus minus times Z and times S to Z. So what is this A1? So this A1 plus minus. This A1. This is C star actually. Yeah, X with C star, A lambda. On a quantity A1, just by either multiplication with lambda or by multiplication with integers. Okay? So this turns A1 into a C star and manifold is C star. Variety is C star actually. So and concretely, what we said classes concretely then just X in Z, P in Z2, such that X gets attracted to P. When I act is lambda, and then lambda will be 2. That's why I want to see attracting cells or this attractor as pairs of a fixed point plus something which is okay, yeah.
But in its characterization of C, that S should have trivial.
Yes.
Or is that?
Yes, here it is.
Okay.
Thank you. Yeah. Okay, good. So now I make a diagram as follows. Can I still write here? Yeah. So I have my Z plus, and I have my Z0, and I have my Z. Yeah. So what I can do, I can project onto this point X. So this is my P class. So we just project the points. I can do the same thing for Z minus. And then I can do the other projection, that's Q plus and Q minus to the fixed point. And of course, I can include the fixed point. You know, by just saying my fixed point P goes to P, which has element. Okay, now I have this diagram. And so by abstract, decomposition, our set decomposes the union over sets complete. P plus the W is in Z0. This is the attracting cell that I pick this G. Okay. So what are these guys in our special structure of Grassmannians? So in a special example of in the Grassmannian, it's one. Let's say 2, 3, so 1 and 2, 3. So then you have fixed point notation in terms of column, then you see a spot. So this is column 2 and 3. And then the negative attracting cells means I can put any star below, and the positive ones I put any star up. And here I don't put anything because the linear combination is the last column will kill this star, and the linear combination is the first column here. And so what I just told you here is the standard definition of cells in the Grassmannian. And I just want to emphasize it's a negative cell or positive cell depending on attracting model. Okay. So good. So now what I want, I want to have an algebra structure around that everything. So first thing is I can look at Z plus and Z minus, 5 of what does with Z. And I want to take probability of that. And let's say I take the closure of that. So in the special case,
You look from below, Catharina, apparently it works. So if you look from the bottom of the board. All right, maybe not.
oh, good sense. So I want to give algebra structures on these things. So what is this? It's in practice, this is homology of set corresponding to a fixed point W minus plus closure intersecting this point W prime plus and the sum of all W. Yeah, so that's a kind of thing that I want to have algebra structure. Second thing I want to think about is I take homology of Z plus the minus. If I will put that to the set, the minus Z plus, if I mix minus and plus, which is nothing else than having homology of Z minus corresponding to total fixed point W intersected with Z plus corresponding to W minus. That's something again of W points, and these are inside sets.
What's the closure? What's the closure there?
So let me explain. So we can either take the closure. So let's say what is this in examples. So in examples, the first thing would take intersection of solar like this. In the example of like this. And in the second example, we would take the intersection of open negative attracting sum is open positive one. So these are what people usually call open original. I mean, open and one is I don't have the closure. Okay, so in general they are not compact or anything nice. So I want to take homology with compact. Okay, so these are nice reasonable vector spaces. So these open Richardson varieties, they have lots of generalization just for people who know this stuff. These are special cases of so-called Lie varieties. So I think they were introduced by Mathas in connection with one of the homology. Yeah. So this first example, I want to see in parallel to my motivating example that we look at endomorphisms of projective generators. So in the case when we take here two block Springer fibers, and do this construction, then this is this old result of then match them myself. That we get somehow the algebra. Or if you want, what we can get is symplectic one. So this is how you will fit into this workshop. And so the connection with symplectic one of homology, this is by Asilata and sheaves. So as in the introduction, I want to say this is the stuff which we know somehow in some examples, and I want to focus on numbers. So that is good.
Catharina, is the Z plus bar smooth?
Set this one?
Yeah.
No, two varieties are in general not smooth. You often take a resolution that is technically what someone's resolution. Homology, equivalent homology of such potentials in resolution are exactly equal.
So is it clear why there's an algebra structure?
Second?
Is it clear why there's an algebra structure?
No.
Okay.
No. So it's not clear, nothing is clear. But I don't want to talk about this. Because it's similar to that case, but that case is the newer one. So I focus on that and maybe comment sometimes. Okay, so we want to understand this thing out. Good. So now, what do we know about this space? So if I intersect this ZW minus and ZW plus, if you look at this example here, if I would intersect two such open things, if the ones are the same spot in both cases, you can maybe easily see that the intersection turns a point. Right? So if the ones are somehow, if this is far up and the other one is far down, no, if this is far down and the other one is far up, then they have no intersection because it's far down. Right? So that means what you can immediately see from this here, that this space is zero except when it's directed. So W has to be smaller than W, but maybe vice versa. And so this is exactly the behavior of Böhmer modulus or standard modulus in the highest wave category, because standard modulus form an exceptional segment. So you have X only in the direction of the partial orbit, and you have endomorphisms only the triple ones, identity or scalars. So that means we expect here that this is somehow looking like the exchange of our standard options. Okay, good. So now I want to give a setup where we can put an algebra structure on this. So what is the algebra? So, and for this I have to do abstract nonsense, or want to do. So these Z should be any derived category of the following form, but these should be any formalism of constructed sheaves. Sheaves on side. This sigma performance. So we can put that push forward, etc. So this could be so construct the sheaves on the analytic space, analytic space of sets with coefficients in any way up. You can do that, or you can do analytic versions, construct the sheaf on set over Q, coefficient. Or you can do mixed motifs, which we also saw at this conference. Whatever you want, you just want to have some constructed result and you want to fix that. Okay, good. Now, if I have this abstract nonsense, I can define the analog of Böhmer objects. For standard objects, it is very good. And for people who know how to define standard objects using the more constructions, they should find it very natural. Let me just define it. So I define delta will be the following thing. So I take Q. This is the constant sheaf on Z0, and then I take Q plus start, so I put it back here, and then I push it forward via P plus down there. So that means this is an object which is indeed set the construction. So and I start this space which is just a finite collection of fixed points. So it's just a collection of points. I take the constant sheaf on there. So what I get, you should think of as being a direct sum of standard objects, and I denote this direct sum. Yeah, so each sum corresponds to one sum. Okay, good. And then the third, right? So first thing, so if I take forms in this divided category, totally abstract. This is only multi. Look, this conversion is compact to power, so minus 5 of what I would say. So plus S weighted. So first of all, it's only as a vector space. But as soon as you have here some kind of weighting, either via mixed Hodge or via Chow motifs, it fits and gives an isomorphic of weighting vector spaces. And secondly, is there's a convolution algebra structure on the right hand side. Making this an isomorphic problem. Okay, so let me comment a little bit on this one. Let me don't want to solve it. Okay. So in the special case of normal modulus, an ordinary integral O, this number one is actual it's reach so we generalize the framework. So they just calculated this by hands, using their specific setup. But actually, one can do it in this general setup. So I see this as a general setup for the special results here.
Sorry.
Yeah.
When you say special perverse, you mean
So I think mean black white T, G would be, and I think the technical.
Yeah.
That's what the sheaves. This is sheaves. Okay. So right. Second thing is I want to say what is a technical tool which is used for the proof. I don't want to give the proof, I want to give a technical tool. And so if you look at the definition of this delta, it involves the Q plus and the P plus. So I could also have taken Q minus and P minus, and then I would more or less take the dual lemma. So this is just a choice I make. But if you look at the right hand side, it has a minus and a plus. So the left seems to be only plus plus, and the right seems to be only the black mix. And so it seems to be strange. So and the main point behind this is the following result of Braden. So it's called Braden microlocalization. Yeah.
I would say.
Oh, hyper. Okay, so what does it say? So it says the following: that P minus upper star, Q minus over 3. This is equivalent to P plus upper 3 and Q plus lower star. As functors form a subcategory of my category I'm working with to the divide category corresponding to the right Z zero. So this is already a nice thing. So it connects sheaves on Z with sheaves on Z0. That's a good thing. So via these functors. So this is just a category of monatomic sheaves. So this monatomic is in principle a very easy condition. So we have C star acting on Z. So I have an action map and I have a projection map. And I want to call the sheaf monatomic if action map is like same thing as projection map. And I should do this. So sheaf is monatomic if this holds, and this is just a triangulated subcategory generated by these steps. And so it's a natural condition when we talk about sheaf star equivariant. So it's a nice subcategory. And so why is this useful? So this is useful because when I compute these terms in this category, I can use a junction and move my P and Q to the other side. So they give other P's and Q's with maybe shrinks and stars, but it's always plus. But then I use this equality here, and I turn the middle two pluses into minuses, and I take the left two guys by a junction again to the left, and what I get is something which looks like minus plus minus. And this is somehow why it goes. Yeah? So move two pluses to the other side, then change the middle pluses into a plus and minus, and move two guys back to the left, but they turn now into plus and minus. Okay. Good. And what is the second ingredient? The second ingredient is Maybe I will here. The second thing is use a quick way to read. It's okay. Okay, so you interpret text. Interpolation. Space. So I don't want to explain really what this space is, but it's a space sitting inside A1 times Z times Z. And so I have the protection to A1. And I can in particular build something like Z tilde, final product over Z is Z minus, and final product over Z is Z plus, because I have these two projection maps to Z, which defines this final product. And then everything fits still over A1. And then the idea of this space is that it interpolates between the thing which I would write down on the left-hand side of a product, for this kind, and the right-hand side of the product. And abstractly, one can then do, so this defines that and convolution. So well, it's pretty complicated. There's some whole specialization map involved, etc. And it's hopeless for me computers. But it's abstract nonsense, which just when you look at this kind of definitions, in particular, have the chance to work absolutely in a DG setting, infinity setting, A infinity setting, or whatever. So it's totally general. So, but now the question is, can we make this somehow complete? So that's what I like to mark construction. Oops. Another thing is DG just have not columns or multi, but rather spaces and corresponding projects. Okay, but let me make it complete. So I want to look at the case of black writing now. Black writing. So when I look back to this kind of Grassmannian, we have this very nice parameterization of cells by these stars. So every cell is an Arkham space, and so we know exactly how to parameterize these stars by acting with the uniforming group on the corresponding interpretation matrix, viewed as an element in the corresponding space. Yeah, and so this I want to use. I want to use parameterizations. Set class. Okay, so let's try to do that. Okay, so what do we know? So I can take UW. So this is U that's standard uniformity group. And I want to take black lines of right? No, I don't. No, I don't. So this is standard uniformity. And so I accept this with W. That's in this section. So this is my UW. And so my parameterization is the standard parameterization. I can call UW isomorphically UW and W P modulo T. And this parameterizes for me myself. And there's nothing else than CW plus in my data. And I can do the same thing with W minus. I just replace here, this is the opposite standard parameter, and I get an opposite. The negatives. So then it's in principle, I can say, okay, the cell just corresponds to certain elements in matrix. And now I need to write this convolution product in terms of matrices. And so the point is, I want to mix the positive C plus and C minus, it's Richardson, Richardson. So I want to mix UW and UW minus. And also for different W's. And here's the lemma. Our technical lemma, but it's the key point. I take UW and do UW right. I have a map to set by just sending it there. So I fix W and I take the product times P. So that's the obvious multiplication, and I can do this in the opposite direction. Well, you find going to U bar 1 to U bar W. So these are two multiplication maps, and the statement is that the image is agreed. And actually, there's a map which identifies this space, such that this diagram. So in other words, I find corresponding to U and U bar and U bar prime and U prime, such that these two things. And in case of the Grassmannian, which makes everything easier, the U bar prime is the same thing as the U bar, and the U is the same thing. But you can just swap it, but in general you can't. But you can write any such product in here as a product in the limit.
W prime here on the right side.
W prime is what?
On the left side is the W prime. W
Oh, sorry, I don't want to.
Okay.
So I want the same W.
The same W.
The same W everywhere. The prime is only referring to the. Right. I want to put a minus here and a minus here. So I want that the U and the U minus versus U minus. Yeah, and the claim is I can multiply two guys together in both orderings, and I get the same set. And I have a bijection between these products and the other. Okay. So, and what does it give me for me? So this gives me a map from Z minus times Z plus over Z. So that's my union of Richardsons, open Richardsons. Type of product over Z before. It's 2 minus. So you should think of this as being a map which is supposed to give us a multiplication. And I can just explicitly write down this map by taking an element Z minus here, UW, P1 P, U bar, W, P, Z plus. And you just want to go from this plus minus to minus plus by swapping these two guys. So I just write U bar prime, U, and then W. Union, so that's the minus part, Z plus U minus U prime. So the point is I have a U here and a U bar here, and I swap them via this map upstairs to a U bar prime and a U prime, and I just multiply this corresponding minus. Yeah, so I just want to swap into guy in the middle and the rest of the office. So this gives you a map like this, and so then the series, okay, the induced map So the use map one homology, so I take homology of this guy. 7 minus 7 is 7 plus tensor this homology. Well, 7 minus 7 plus, which I identify with the homology of this left-hand side. It's not here. Yeah, the map. So homology of the left-hand side. Reduced by this part. And so the induced map agrees with the edge shapes. Well, so and the whole thing is now written in a way where we really compute. So we really explicitly compute in this parameterization and can write down these maps in these examples. Okay, so let me then go back to the Grassmannian case. So this is how the Grassmannian case. And the question is, how does the algebra look like in this case? So what we do now is for any we take our convolutions. Sum them up, we take this corresponding convolution product, and then this underlined now, I computed the result at some point. The result looks like this. Here's the curve. And you see always double errors. One of the errors would be wrong. So this is the wrong in two polynomial ones, and the other we didn't want to next. But you see it's always coming in pairs. There are some explicit relations, which I don't want to mention, but some compositions are zero, and these diagram products. Okay, so this is the result which comes up, and we at that time also computed some multiplication for the ANZ structure. To explain how this function form C in this geometric structure, for instance, and how can we generalize this to something which is not because we made it before. So here's an answer. So what I want to do now, I want to describe this X, which I see as this homology, via what I call the pilot. And I call this pilot once because I'm thinking that these things are really because one is diagrams which in this side of Smith, the one of the pilot Kennedy is computing this. So what do I want to do? I want to say, okay, I will choose the picture for a given X. So X is a forward space point where I just choose these two standard base vectors, in this case 1 and so I have the point from the y 2 and 4. And so this is the boost, and then the rectity now fixed point given by the coordinate vector 1 and 3. And I want to draw an intersection by just connecting these red lines together. So that's it. And then I can use a rule construct from this vector space, which has the basis as follows. So my basis is just I take blue and I want for each red and each blue line, I want to have an intersection point marked. For instance, here. Yeah, every line has exactly one intersection point marked. And then in this case, there is of course two possibilities. I can either mark here or I can mark, no, in this case only one. I can mark this guy and this guy. But I have two ways of marking. It's either a fill dot or it's an empty dot. So altogether I have four. Okay, and why do I want to make this? I want to make this because when I compute this corresponding efficiency, geometrically it's a C star times C star. And if I compute this homology with contact support of C star times C star, I get exactly something four dimensional. And each dot, the black and the white dot, represents one homology class for C star. And so taking two pairs is exactly giving me the four possible homology classes. So there could it happen that these coordinate spaces overlap. So here's an example where the blue and the red thing have a common coordinate subspace. Then I don't want to put any markers on this because it somehow sticks together at the top. This counts like as a marker. So in that case, I have only this possible intersection one. Again, I put the filled one and not filled one. And if you compute what this Richardson variety is. So it could also happen that you have a picture like this, which more or less looks like that one, except that there is a point in between which I didn't take. So if I don't take a point, so that means I have an intersection point here, but I didn't take the stuff before, I have to mark it. And this marker geometrically means I put an A mark. And you can check that this Richardson variety takes this down. Okay. So that is something like this. Where I have, so in these examples, I had only one way to choose the intersection points, but here I can either choose this intersection point and that one, or this one and that one. And so I have this little square. And this little square is indicating that something interesting is happening, and this is where the higher structure comes. There we need to have some differential. And I want to explain a little bit where this differential comes from. So let's just play that stupid old game. So we mark in all possibilities. So the four pictures at the top, they have the markers at the top left and bottom right. And these pictures have top right, bottom left. And I do the old rule that if I miss here a point, which I could have taken, I put a green cross, and this green cross stands for A1. So these pictures would geometrically mean a C star times C star times A1, and the top would mean a C star times C star. I have this.
But you miss points everywhere. Why do you only put a marker on the?
So I look from the right,
Okay.
and I look which ones I missed, and I got from the. So what I in this way is all these copies of C stars and A1s. And now you might say, what is this rule? And maybe some of you know Eodasans. So this Richardson varieties decompose further into a union, which is a unit of Eodasans. And in this example of this Richardson varieties, this top picture and the bottom picture exactly corresponds to these two Eodasans. So what we write down here is the cohomology of one Eodas and the cohomology of the other Eodas. And how can I compute the cohomology of the space, which is a kind of stratification? It's not needed. It's just a decomposition. It's not a stratification, but at least I can decompose it into two pieces. I want to compute the cohomology by taking these two pieces together. I would write down a corresponding cohomology. And so I put this into context. I put this part and this part, and I just want to put a differential. And if you want to find, I tell you what is this. So whenever you white leg on the left, then there's a map going to this third part on the right. So I have a map from top to bottom, which takes the first this vector to the surface vector to the first. And then I have this side, which is the second base vector upstairs, and also goes to the and I have the last side, which takes the fourth base vector here and makes it the sum of it.
Sorry, I somehow missed how you get the pictures from you have this parameterization.
Yeah.
How do you get the picture from the just the if you write it as columns and a matrix?
So the pictures I get from these columns, that's a bit, so it's a bit tricky. I can roughly say what you do. So what you want to do to compute an intersection here, point in the intersection, you want to somehow translate these one into something over here via an invertible matrix. And I take this invertible matrix, that's in this case a 2 times 2 matrix, and embed it into GL 2 times 2 matrix. See that element there. And I can somehow decompose this there with respect to the three-line composition. And this information is hidden in these pictures. So what you see here is roughly a 2 times 2 matrix. And I draw permutation matrices, but look in the dots right here. This time maybe somewhere. So this top four would be one reversal, this would be another reversal. And I have a differential whenever I increase the value for the permutation by one simple relation. Yeah. And so the claim is now generalize it, just draw for arbitrary Grassmannians this kind of same conclusion. But the rule is somehow given. Good, whenever you have these squares, these differentials, but these squares can be huge. They can be also nested in each other, inside each other. So for instance, I can take 3 blue lines and 3 red lines, and I have many squares which I build, but every square I put these rules. And the claim is these diagrams give a diagrammatically defined graded vector space. The grading comes from interpreting these dots and the stars using homology of C star. Here, respectively, this guy using homology of A bar.
And when you say by for every square, you mean for every like rectangle without interior or something?
So for every situation like this, yeah, then I have that. Alright. For every local situation like this, I have
Local as in ignoring the other strands or
ignoring the other strands. Yes,
ignoring it.
ignoring the other
So
strands.
every rectangle.
Yeah. And then I always have these 2 points, which I have to see as the identity in an S2 symmetric group, and the other 2 points. And then this I have this local picture.
Okay.
Yeah.
Is it any time you can have it yes in and put it down?
Exactly. So I think of it, and this is how I came up with the pictures. That's the real answer to Vanessa's question. So I think of it as some Lagrangians, the red and the white ones, and I want to ask how many holomorphic picks this is. This is what I count. Of course I don't count, but this is what I want to mimic. And so I just want to say the degree of this dot. Or this dot. So this guy is 1, and this is 1, 0. And the degree of the crossing is also 1. Putting this gives a grading on these pictures, and so I get a grading vector space diagrammatically, and this thing to define a PG algebra structure on this graded vector space. And you see on this that this is a PG version of this X algebra coming from perverse sheaves on the between centers. Okay. So parabolic normal modulus or maximum parabolic for GLM with parabolic subgroup. Yeah.
So maybe questions, which one of these degrees is the cohomological?
Yes, so the first one for me is the cohomological degree, and the second one is the internal degree. So what I wrote down for you, these are the degrees, which are the geometric degrees. So unfortunately, when you are used to solve the bimodules, you would not like that. And the reason is the normalization for me for solving bimodules or category O is that heads of projective and heads of normas are degree 0. And in this degree version, the Roma shifted by minus the length of the labeling element, which is very annoying. So the algebraic degrees are, this one is 0, 1. So it's a whole into the right, and the other one is 1 minus 1. So the x1 in degree minus 1, and so this is that dot, and that's the so that means if I look back to my quiver, this quiver here, I have always a point in degree 1. So this is somehow the obvious map between neighbors or numbers, which one is this, and then there is an x1 of degree minus 1.
Should I be thinking about opposites between like standards in some categories, singulars or real bimodules?
No.
Or in
yes.
this would be like two label.
Uh, no, you can't model it by a single zone diagram. So you have to think of it as arms between regular solid diagrams, but taking motion.
Oh, you do parabolic?
Yeah, I don't have what it. That's not always proper.
Everything is.
So really, the algebraic for this is the cyclotomic portion of the virtual which is the PLR, the short version of PLR of level 2. And inside there's some dimensions.
Is this, would this be related to SL single homology or SL, I mean,
As a moment.
yeah,
As a moment. Okay, so it means what I just want to say again, we can explicitly write down this multiplication, you can compute everything explicitly, and it agrees this both with this parameterization convolution product structure and with the abstract prefix Categorification interpolation. And so I was